In this comprehensive and expanded lesson, we will navigate the profound evolution of physics from Maxwell's electromagnetism to Ehrenfest's bridge. We will explore time dilation through detailed spaceship examples, the breakthrough of massless particles, and their inherent momentum, the revolutionary de Broglie wavelength, and the specific mathematical operators that define Schrödinger's wave mechanics. Our goal is to see how these seemingly disparate theories form a single, elegant journey from the classical to the quantum. Hello everyone, I am Professor Ganesh. Today we delve much deeper into our quantum journey. We start by examining how Maxwell's work on the constancy of light set the stage for a relativistic revolution, forcing us to rethink the very nature of space and time. As an engineer, I find it fascinating how these universal laws, first derived in the laboratory of the mind, now underpin the very technology we use every day. This wasn't just a technical shift. It was a fundamental change in our perception of reality. Maxwell famously showed that light is an electromagnetic wave traveling at a constant speed, denoted as c. This invariant speed, which emerges naturally from the permittivity and permeability of free space, became the foundation for Einstein's special relativity. It implies that the laws of physics must remain identical in all inertial frames of reference, leading to staggering consequences for how we measure time and distance across the cosmos. Maxwell's equations were the first step in unifying the forces of nature. Consider Einstein's famous thought experiment involving a high-speed spaceship. If a spaceship travels at a velocity of 200,000 kilometers per second and emits a light pulse at its own relative speed of 300,000 kilometers per second, classical intuition suggests a stationary observer on the ground would see the pulse at 500,000. However, Maxwell's equations and Einstein's relativity prove this is impossible. The speed of light remains exactly c for everyone, regardless of their motion. This absolute constancy of light speed implies that space and time themselves are not absolute. As the spaceship approaches the speed of light, time must dilate and lengths must contract to ensure the speed of light is preserved. This is time dilation, a fundamental prediction where time appears to slow down for the moving observer. To an observer remaining on Earth, the spaceship's clock would appear to tick significantly slower than their own stationary clock. Space and time are flexible, but c is not. Einstein's derivation of the total relativistic energy, E, revealed the profound realization that energy and mass are equivalent. As an object's velocity approaches infinity, an infinite amount of energy is required to accelerate it to the speed of light. But what happens when we look at particles that have no mass at all, like photons? This brings us to a critical realization in particle physics regarding the energy-momentum relationship, where classical mechanics simply fails to provide an answer. For massless particles, the energy-momentum relationship simplifies to the elegant E equals pc. This means that even without mass, a particle like a photon possesses momentum that is directly proportional to its energy. This was a profound shift from classical physics, where momentum was strictly the product of mass and velocity. In the quantum realm, momentum is a fundamental property of the field itself. Crucially, it is important to remember that momentum and energy are not conserved across different inertial reference frames. Only mass remains invariant, a fundamental property we will explore in the next scene. This understanding of momentum led to Louis de Broglie's major breakthrough, the de Broglie wavelength. He proposed that every matter particle has a wavelength inversely proportional to its momentum. This wave-particle duality is not just a theoretical curiosity, it is a fundamental truth that serves as the heart of the quantum mechanical wave equation. It tells us that mass is a fundamental invariant, a principle that allowed physicists to determine the mass of the Higgs boson in 2012. We are all, at our core, waves of probability. Erwin Schrödinger took these wave-like properties and developed his famous wave equation to describe the quantum field. To truly grasp its power, we must examine the specific mathematical operators that allow us to calculate the energy and the dynamic change of the quantum state over time and across space. These operators, the Hamiltonian, the time derivative, and the spatial Laplacian, are the keys to unlocking the physical reality hidden within the wave function. The Schrödinger equation applies the Hamiltonian operator representing the total sum of kinetic and potential energy to the wave function. It balances the energy landscape expressed through the spatial derivative operators on the left against the rate of change of the quantum state over time on the right. This describes how the probability cloud of a particle evolves as it interacts with its environment, completely describing the quantum particle. But we are still left with a burning question that puzzled the greatest minds of the 20th century. If everything is made of atoms that obey these probabilistic quantum laws, why don't macroscopic objects like baseballs or planets exist in superposition? Why does our everyday world appear so deterministic and solid? How do we cross the boundary from the microscopic to the macroscopic? This brings us back to Ehrenfest's theorem, the essential statistical bridge that connects quantum weirdness to classical predictability. Paul Ehrenfest proved in 1927 that while individual particles are indeed smeared out in probability clouds, their average behaviors, what we formally call expectation values, actually obey the same Newtonian laws we know from classical mechanics. By averaging the quantum fluctuations across many states, we arrive at the familiar, predictable physics of the macroscopic world. Think of it as the center of mass of the probability cloud following a classical path. This is the stochastic correspondence principle that unites our two worlds. Ehrenfest's first equation formalizes this bridge by stating that the average position of a quantum particle changes at a rate equal to its average momentum divided by its mass. This is the direct quantum analog to the classical definition of velocity. It shows us that even in the heart of the quantum realm, where everything is probabilistic, the core relationships of motion that we observe in the macroscopic world are perfectly preserved. The average position changes exactly like a classical particle. These deep derivations rely on the formal vector identities used in both engineering and physics. Whether we are calculating work as the dot product of force and distance, or torque as the cross product of radius and force, the mathematical structure remains consistent across both classical and quantum regimes. These identities are not just mathematical tools. They are the language that allows us to translate the physical reality of forces and energy into the quantum landscape of operators and wave functions. They reveal the underlying symmetry of the universe. Finally, the second Ehrenfest equation proves that the average momentum of a quantum particle changes at a rate equal to the average force acting upon it. This derivation confirms that Newton's second law, the cornerstone of all modern engineering, is simply the statistical limit of the microscopic quantum world. The rate of change of momentum equals the negative potential gradient, exactly as we see in classical mechanics. The two worlds are not separate. They are one unified field of all possibilities. We have seen the elegant unity of physical law, from Maxwell's light waves to Einstein's relative time, through Schrödinger's probability clouds, and finally back to classical certainty through Ehrenfest's bridge. I hope this deep dive has enriched your understanding of the universe. For more on how these universal laws apply to the challenges of everyday living and help us manifest our potential, I invite you to explore my book, The Engineering of Life. It is a guide for anyone seeking to understand the laws that govern our existence. Thank you for joining me on this quantum journey. In our next session, we will explore practical engineering applications of these universal principles and how they shape our modern world. I am Professor Ganesh, and I look forward to seeing you then. Take care, keep learning, and keep exploring the field of possibilities that surrounds us all.